Have you at any point contemplated whether we're genuinely alone in the universe? Or, on the other hand, if there's something else to our reality besides what we see? Consider the possibility that the James Webb Telescope at long last demonstrates that we live inside a black hole. Join us as we find out more about this weighty news that will make you question all that you thought you had some awareness of the universe. So, what precisely are black holes? They're like something out of a bad dream. Sure, you could have seen them in science fiction motion pictures, but in reality, they're significantly more unnerving. They're not just dark. According to researchers, totally black holes in space are, in reality, enormous amounts of matter fit into an extraordinarily little region. Consider a star multiple times more enormous than the Sun, all packed into a circle the size of New York City. The gravitational pull is serious to the point that nothing, not even light, can escape from it. Researchers have been captivated by black holes for a long time. From that point onward, they considered objects in space so enormous and dense that they could trap light. The most well-known thoughts regarding black holes were predicted by Einstein's hypothesis of general relativity. Basically, when a huge star kicks the bucket, it leaves behind a minuscule, dense center. If this center's mass is multiple times that of the Sun, gravity overpowers everything else, prompting the development of a black hole. Identifying black holes is no simple task, since they radiate no light. However, researchers have tracked down approaches to construe their presence by noticing their consequences for neighboring matter. For instance, if a black hole passes through a haze of interstellar matter, it'll pull the matter towards it in a cycle called accretion. Furthermore, when an ordinary star gets too close to a black hole, it can get destroyed, emitting X-rays as it does so. Black holes also have a critical effect on their surroundings. They can consume nearby stars, radiate strong gamma bursts, and even impact the development of new stars in certain areas while slowing it in others. But where do black holes come from? Picture this. A star, once great and bursting, meets its extreme downfall in a stupendous blast called a supernova. From the remnants of these fallen giants, black holes arise. Most black holes are conceived from enormous stars that have reached their divine retirement party in a supernova. Smaller stars, when they die, change into something many refer to as neutron stars, which are really dense but not dense enough to trap light. However, if a star is multiple times the mass of our Sun, it falls under its own gravitational pull, forming a black hole. As these strong stars break down, something abnormal happens close to their surfaces. Time itself begins to play tricks. From the viewpoint of somebody far away, time seems to dial back near the event horizon, the final turning point for anything falling into a black hole. It's like the star's clock ticks at a different speed compared to our own. Now and then, when two smaller black holes collide, they join to shape an even much greater and more frightening black hole. If a black hole interacts with a neutron star, they create a giant nightmare that defies comprehension. Researchers have been wrestling with the size of these enormous phenomena for a long time. Black holes come in two sizes, gigantic and small. There's a vile secret surrounding them that we just can't unravel. But here's the twist. Small is relative when it comes to black holes. Supermassive black holes, remnants of gigantic stars, can be as enormous as 10 to multiple times the size of the Sun. There could be upwards of 10 million to a billion of them in the Milky Way alone. That's a galactic number of black holes that could swallow anything in their way. But wait, there's something else. Supermassive black holes are on the opposite end of the spectrum. They're millions, if not billions, of times bigger than the Sun. They exist at the center of enormous galaxies, including our own Milky Way. It's like a vast dead space that is pulling everything towards it. Eminent physicist Stephen Hawking talked about black holes throughout his life. His lectures were always clever, but some of his theories couldn't be confirmed due to an absence of vital gear. Anyway, there's hope not too far down the line. A single scientific instrument is changing everything, and we're not ready for it. It goes by the name of the James Webb Space Telescope, otherwise known as JWST, and it's here to dive into the depths of our universe. Let me tell you, the JWST is no ordinary telescope. It's an engineering wonder, a demonstration of the capability of human desire. Sure, we've sent off other space telescopes before, and they've been going about their jobs just fine, But this bad boy is in a class of its own. The JWST makes the Hubble, which has obediently served us for a long time, look like a simple bit in the universe. The sticker price of this cosmic miracle is an incredible $10 billion. Yes, you heard that right. That's an adequate number of zeros to make your head turn. And get this, it took the combined efforts of NASA, the European Space Agency, and the Canadian Space Agency to rejuvenate this wonder, not to mention the priceless contributions from over 300 universities. However, we must not disregard the dangers that accompany such an excellent endeavor. I know this isn't an adventure for the weak-willed. The JWST is wandering into an unknown area, pushing the limits of what we know and taking us to places we've only dreamed of. Following a successful launch, NASA recently reported that the telescope has sufficient fuel to endure more than twice its base mission life expectancy of 10 years. Since its launch, the JWST has made numerous unimaginable accomplishments. It traveled more than 1 million miles to reach its orbit around the Sun, where it will dwell forever. During its journey, the telescope successfully unfurled its huge 5-layer sun shield and its giant primary mirror, both of which had to be folded to fit onto the launch vehicle. Now, after NASA has calibrated and aligned it, the telescope is practically all set for full activity. A most intriguing aspect concerning the James Webb Space Telescope was when NASA announced that it had captured its first pictures of starlight. The primary picture taken by the telescope was of a star called HD 8446, resulting in a mosaic of 18 dispersed brilliant spots from a star's light captured by the 18 mirror segments situated on the primary mirror. NASA delivered a better-than-ever image of HD 8446 in which 18 unfocused duplicates of the star were united in a purposeful hexagonal formation. Once the observatory effectively adjusts the individual segments of the primary reflector, it will begin the image stacking process. This will overlay 18 images on top of one another into one clear view. Thanks to its complex technology, the JWST will assist researchers with examining the beginning phases of the universe after the Big Bang. It will concentrate on what worked out after the first stars formed, a period known as the epoch of reionization. This period alludes to when neutral hydrogen was reionized or made to have an electric charge again by radiation from these first stars. This involves looking back billions of years, which is only possible with a powerful telescope like the JWST. The telescope will also help researchers find exoplanets, which are very hard to recognize due to the way they interact with their host stars. Its strong sensors will actually want to notice these planets in more depth, including, in some cases, imaging their atmospheres. Figuring out the atmospheres and development conditions for planets could assist scientists in better predicting if certain planets are tenable or not. Aside from concentrating on the assembly of galaxies, researchers will concentrate on worlds to perceive how matter is organized on a massive scale. This, in turn, allows us to see how the universe evolved. The twisting and swirling galaxies we see today emerged from various shapes over millions of years. One of JWST's objectives is to look back at the earliest galaxies to better understand that evolution. Researchers are also trying to figure out how we got the assortment of galaxies that are visible today and the ongoing ways galaxies form and gather. However, above all, the James Webb Space Telescope will help us answer the most significant inquiries of all. Are we alone in the universe? And are we living inside a black hole? The JWST has already been on the chase, and guess what it found? Compounds called polycyclic aromatic hydrocarbons, PAHs, lurking around those enormous supermassive black holes in 3 active galaxies. PAHs are carbon-based molecules with ring-like structures, like the goth children of the universe. They're everywhere, from distant galaxies to comets in our solar system. Now, they're not just intriguing because they could be the building blocks of life, but also because they help astrophysicists track star formation. When ultraviolet radiation hits these PAHs, they get all fancy and produce infrared light, a sight that can be detected by the JWST's mid-infrared instrument, also known as MIRI. That is normally a sign that there are some hot, young stars nearby. But wait for the unexpected development. A daring astrophysicist, Ismael Garcia Bernard from Oxford University, decided to take a look at 3 active galaxies known as NGC 6552, NGC 731, the creepily renowned Stephan's Quintet, and NGC 7469. These galaxies are a multitude of light years away in the depths of darkness. Now, what Garcia Bernard found will make your hair stand on end. In those focal regions where the black holes rule, he found an overflow of PAHs. Sounds great, right? Well, here's where it gets chilling. The radiation close to those very monstrous black holes turned the PAH's very essence. It changed them into larger, electrically neutral versions of themselves. The smaller, electrically charged PAHs evaporated into insensibility, like being depowered by the very darkness. But wait, there's a promising sign. The larger PAHs managed to endure because they found cover inside thin, dense gas-filled clouds. It's like they found their own protective hiding spots. So while supermassive black holes are expected to eat up everything around them, they leave behind some signs, like footprints in the cosmic sand. I know what you may be thinking. If black holes can do all of this, might it be conceivable that our universe is inside a black hole? Could the solution to the question that has tormented humanity for eons finally be readily available? With the James Webb Space Telescope, we may soon find out. The telescope will plunge deep into the mysteries of our universe, and who can say for sure what it will find next? As the James Webb Space Telescope, JWST, begins its mission, it vows to alter how we might interpret the universe in ways previously unimaginable. Its cutting-edge technology offers an unprecedented view into infinite phenomena, possibly uncovering mysteries that have eluded researchers for a long time. One of the key areas the JWST will investigate is the development and evolution of the first galaxies. By looking further back in time than at any other time, the telescope will be able to notice the early universe's conditions and the cycles that led to the formation of galaxies. This examination could provide insights into how the universe progressed from an almost uniform state to the rich tapestry of galaxies, stars, and planets that we see today. Grasping these early phases is significant for sorting out the history of cosmic evolution and the origins of the structures we see in the universe. The JWST is also prepared to study the mysterious dark matter and dark energy that make up a large portion of the universe's mass energy content. Although these components can't be observed directly, their presence can be inferred through their gravitational effects on visible matter. By observing the behavior of galaxies and galaxy clusters, the JWST can help map the distribution of dark matter and provide clues about the nature of dark energy, which is believed to be driving the accelerated expansion of the universe. This could lead to groundbreaking revelations in how we understand the fundamental forces that govern cosmic dynamics. Another intriguing part of the JWST mission is its capability to identify and analyze exoplanet climates by studying the light that passes through a planet's atmosphere when it transits its host star. The JWST can identify the chemical composition of these atmospheres. This includes detecting molecules like water vapor, carbon dioxide, and methane, which are crucial for assessing a planet's habitability. The ability to examine exoplanet atmospheres in detail may help researchers identify planets that could support life and prioritize them for further study. In addition, the JWST's high-resolution imaging capabilities will allow it to observe the intricate structure of star-forming regions. These areas, often obscured by dust and gas, are where new stars and planetary systems are born. By looking through the dust with its infrared sensors, the JWST will uncover the complex processes involved in star formation and the evolution of protoplanetary disks. Understanding these processes is essential for appreciating how stars and planetary systems, including our own, came to be. In addition to its scientific goals, the JWST is expected to inspire a new generation of cosmologists and space enthusiasts. Its stunning images and discoveries will capture the public's imagination and highlight the importance of space exploration by showcasing the universe's beauty and complexity. The JWST will serve as a reminder of the vastness of space and our place within it. The telescope's mission is also a demonstration of global collaboration and the collective effort of thousands of scientists, engineers, and researchers from around the world. The successful organization and operation of the JWST exemplify what can be achieved when nations and organizations work together toward a common goal. This spirit of cooperation not only advances our understanding of the universe but also fosters goodwill and collaboration among countries. As the JWST continues its journey, it will undoubtedly encounter new and surprising phenomena. The data it gathers will likely lead to questions and discoveries that challenge our current understanding of the universe. Each finding will build upon the previous ones, gradually creating a more complete picture of the cosmos. In the end, the James Webb Space Telescope stands on the brink of revealing significant insights about our universe. Its observations will broaden our knowledge of cosmic origins, the nature of dark matter and dark energy, and the potential for life beyond Earth. As it ventures into the unknown, the JWST will not only advance scientific knowledge, but also inspire wonder and curiosity about the universe we inhabit. The journey of discovery is just beginning, and the telescope's mission represents one of the most ambitious and exciting scientific undertakings of our time. The James Webb Space Telescope is set to tackle a multitude of scientific challenges and questions that have long intrigued astronomers. One of its remarkable objectives is to shed light on the processes behind cosmic reionization, which occurred about 13.8 billion years ago. During this era, the universe transitioned from a state of murky darkness to one filled with light as the first stars and galaxies began to shine and ionize the surrounding hydrogen. The JWST's infrared capabilities are critical for studying this epoch, offering insights into how and when the first light arose and how it influenced the development of the universe. Moreover, the JWST will investigate the nature of supermassive black holes and their formation. Understanding the growth and evolution of these massive structures is essential for explaining galaxy evolution, as they are believed to play a significant role in shaping their host galaxies. Observations from the JWST could reveal how these black holes interact with their environment and potentially trace their origins back to the earliest cosmic times. Additionally, the telescope's ability to study nearby planetesimals, water-rich regions, and distant objects will enhance our knowledge of planetary science and the formation of our own solar system. By analyzing the compositions of distant comets and asteroids, the JWST will provide valuable data about the building blocks of planetary systems, offering clues about the early conditions that led to the formation of planets like Earth.